Hey geometry friends, we are in chapter 8 looking at section 8.2. We're going to talk about today the Pythagorean theorem and its converse. So, what is a Pythagorean triple? Let me go back a little bit. I'm going to start off with, even though our text asks us to start off with Pythagorean triple, I'm going to start off what a Pythagorean theorem is. The Pythagorean theorem refers specifically to right angle triangles, and right triangles have three different sides, as all triangles have three different sides, and they have different names: hypotenuse. So these guys that make up the right angle that are perpendicular to one another are called legs, and the side that is opposite the right angle is called a hypotenuse. We refer to each side with a letter. A and B can be used for the legs interchangeably, and C is used for the hypotenuse. Anytime you have a right angle triangle, the sides will relate in this way. You will have A squared plus B squared, I know you guys know this, is equal to C squared. All right, and I know you've seen it before, but I just think it's necessary for us to do that in talking about Pythagorean triples. So Pythagorean triples are when you have um, integers that fit this mold. So the Pythagorean triple that most of us will be used to and think about is 3, 4, 5, meaning I could have a triangle where one side has length 3, one leg has length 3, another leg has length 4, and with that, the hypotenuse would have length 5. So a 3, 4, 5 triangle, let me get my numbers back, would be considered a Pythagorean triple because 3 squared plus 4 squared equals 5 squared. Are you guys with me? And then so I remember us talking about this in class at one time, where if you double or multiply this triple by any by any integer, you will get another Pythagorean triple. So for instance, if I multiply this by 2, each of these terms, I get 6, 8, and 10. And if I multiply this by 3, I get 9, 12, and 15. And I can literally continue, in a sense, riffing off I'm going to call it the parent triple. So Pythagorean triples are a series of 3 integers that fit the mold of the Pythagorean theorem. All right, cool beans. And so here is a more extensive and exhausted form of Pythagorean triples, so you can see that these are the ones that I had down. And I'm going to just refer to these as Pythagorean triple parents. All right, so if you take these as like the parents of the Pythagorean triple, you can generate more by multiplying each of these by some x term. All right, I would take a moment to copy this down, and I'll tell you why, because you will see, well, I'll highlight the ones that you'll see on the SATs. It's crazy how many times you'll see this one, this one, this one less so, and this one even less so. But I would definitely be most comfortable with these guys over here, and just being able to say, oh, I recognize you, you're a Pythagorean triple of the 3, 4, 5 family. Oh, I see what you're doing, SAT people. This is a Pythagorean triple of the 5, 12, 13. Okay, so now that that is out of the way, we see that we have the Pythagorean theorem written down here, which you guys already know and we've talked about on a numerous occasions. You guys remember we actually used the Pythagorean theorem when we were talking about the distance formula, right? Because the distance formula comes straight out of the Pythagorean theorem. So we have all of this. Beautiful, beautiful. We're going to keep it moving by using the Pythagorean theorem to answer the next question. So here in example 1, we're going to find the missing measure using the Pythagorean theorem. Remember, the Pythagorean theorem orients this way. The legs that make up the right angle are called A and B interchangeably, but the hypotenuse is always C. And we know that A squared plus B squared equals C squared. If you don't have this memorized, write this down every time you do a problem. I guarantee you will have it memorized very soon. So as I look at this particular situation over here, would be A, this would be B, and X would be C. So what I'm going to do is I'm legitimately going to replace each of these, like substitution back in the day, right? When you would have algebra problems like this, I'm literally going to just replace it right into the formula. And so 6 squared is 36, plus 15 squared is 225, is equal to x squared. I'll do a little addition. I got 1, carry 3, 4, 5, 6. 261 is equal to x squared. And I feel like this would be 19 times 19, 19 squared. So x is equal to 19. That was wrong. Uh, so it would have been true if we got 361, but we didn't because 19 squared is 361. Sorry, Chapelitos. So for me, I'm going to actually have to take the square root of it. I can leave it as 261 like this, the square root of 261. There is no perfect square. Remember last time we were dividing each radical by, we were trying to figure out if there was a perfect square that divided evenly into each radical, and if it was, then we would simplify it. I don't have the ability to simplify this. I tried, and I was like, oh, no, I can't. So I literally would pull out, I know I'm saying it, the calculadora, and I would put it in, and I would calculate the square root of 261 by putting it underneath the little radical, and you get approximately 16.16 as the answer. Sorry about that. I thought my skills were going to get me. Okay, whatever. All right, so this next problem, we're going to do the same thing. Again, draw quickly a right triangle. If you're still not 100% familiar with the Pythagorean theorem, go ahead and jot that down and then literally substitute, right? So x squared, this time we're looking for a leg as opposed to looking for the hypotenuse. B is 9, C is 11, and so x squared plus 9 squared is going to give me 81, and 11 squared is 121. Subtract. So look at, I'm solving it just like I would any ordinary algebra problem where I'm isolating the variable. So this minus that is going to be 40, right? You can tell me if I'm wrong because I do that sometimes. So if x squared is equal to 40, the square root of both sides, x, is equal to the square root of 40. Remember, I said this last time, if this were an algebra class, I would be telling us to do plus or minus 40. And the reason why is because that's the whole answer, but we can't have a negative length, so I'm not stressed about the negative 40. I can find the square root of this using my calculator, and I would get something in the neighborhood of 6 point something something. And you know why? Because 6 times 6 is 36, and 36 is close to 40. And it wouldn't be like 7 because 7 times 7 is 49, and that's over. You with me? So it would be something in the neighborhood of 6, but since I can simplify this, I'm going to. So the square root of 40, I'm looking for a perfect square that divides evenly into 40, and that's 4. So I would multiply 4 times 10 to represent the 40 underneath the radical. I can take the square root of 4, and I get 2. So my answer is 2 root 10. I know this example took a lot longer than it needed to. Thank you for letting me walk through all of that. Notice that in that last problem, we got decimal answers, right? So, we didn't get integer answers. We started off with integers, but we didn't get integer answers. So check this out. Sometimes we would get Pythagorean triples. And so here, you might remember a Pythagorean triple that had 15 and 12 in it. And so it says, use a Pythagorean triple to find x, explain your reasoning. So I'm going to go back up to our quote-unquote memorized Pythagorean triples. And I want to see if you see anything with 15 and 12. Let's go back. Let me make sure. So 15 is the hypotenuse. That's the longest side. 12 is one of the legs. So we would go back up, or we'd have our, look around for 15 and 12. And you might see it over here. So if you recognize that the Pythagorean triples are often written from smallest to largest. The largest one has to be the hypotenuse, because the hypotenuse is always the longest side of a triangle, of a right triangle, right? Or of a triangle, because you know what I mean. Okay, so you've got 9, 12, and 15. If you memorize your Pythagorean triples, you can come to a problem like this, say on the SAT, and just be like, oh yeah, x equals 9. Because clearly that's a Pythagorean triple. We can check it too. I know you're like, I don't like this. I don't like it. So I'm going to rock out. This would be A, this would be B, and this would be C. X squared plus 12 squared is equal to 15 squared. And with a little bit of work, we can see that thing should work. That looks like a 152, but that's a 15 squared, which gives me 225. And if I subtract 144 on both sides, I'm going to get x squared equaling 12 minus that is going to be 8. Yeah, 22. Yes, I'm going to get 81 over here, which is not done, but you can see that x equals 9, because if I take the square root of both sides, I get that x equals 9. Kind of satisfying, right? It's nice when a thing works out. So you can see that if we use the Pythagorean triple 9, 12, 15, we could have gotten that answer very quickly. All right. So here we have a multiple choice question for us. And I like seeing like a little picture. Like this is one of the standard problems that you'll see with the Pythagorean theorem. You'll see like a ladder leaning up against a wall. And you'll see this until calculus. Like this in calculus, this ladder will be sliding down and you might be trying to find the rate of change in the height and all this stuff. But yeah, this is going to be a common thing, and the Pythagorean theorem will appear a lot in your future math. So Damien is locked out of his house. Silly Damien. The only open window is on the second floor. Don't do it. Which is 12 feet above the ground. Don't do it. He needs to borrow a ladder from his neighbor. If he must place the ladder 5 feet from the house to avoid some bushes, what length of the ladder does Damien need? All right, so 12 feet, 5 feet here, and we want to know how long the ladder is. This is a clear case of Pythagorean theorem. 5 squared, 12 squared is going to be what? If we memorize our Pythagorean triples, we'll know right away that the answer is 13. Obviously, you can let A equal 5, B equal 12, and calculate C for yourself. So we would get 5 squared plus 12 squared equals C squared, and 25 plus 144 is equal to C squared. We'd get that C squared was equal to 169. And I know you've already memorized your perfect squares, so you would know automatically that that was 13 without using a calculator, right? I'm sure you're saying that. Yeah, you would. So this theorem is giving us the converse of the Pythagorean theorem. And the converse basically means you start with what we had as our conclusion, and we go back to our hypothesis. You remember converse, all those statements earlier in the year? Okay, yeah, it's real. Okay, so the sum of the squares of the length of the shortest side of a triangle is equal to the square of the longest side of the triangle. Then the triangle is a right triangle. So the story is, if you're walking down the street, all right, and you see some triangle and you see the lengths of the sides, and you're like, dang, let me check this out. Here's the longest side. I'm going to pretend that's a hypotenuse. And I'm going to square A and square B. And oh my gosh, A squared plus B squared does equal C squared. If you get this result, then guess what you know? You know that indeed it's a right triangle. So instead of starting with the right triangle and saying that the sides relate this way, we're saying if you see any old triangle and its sides relate this way, bet your bottom dollar, you've got yourself a right triangle. Impressive? Let's see how we can use it. The result from that theorem gives us these theorems as well. So what we have here with the Pythagorean inequality is that if you have, now I'm going to start off with the Pythagorean theorem, right? Pythagorean theorem says a squared plus b squared equals c squared. But if a squared plus b squared is less than c squared, then you know, now let me try it again. If a squared plus b squared is greater than c squared, so if a squared plus b squared is bigger than c squared, that's what's being said here, then you have a triangle that is acute, meaning all of these angles are less than 90 degrees. Kind of makes a weird kind of sense if you think about it. Here, if a squared plus b squared is equal to c squared, then we're saying, yeah, see, you the man. Across from you is a right angle. But if a squared plus b squared does not equal to c squared, and in fact is greater than c squared, then it says c is not as big as it needs to be in order to have a right angle. Similarly over here, if we take the idea that a squared plus b squared is equal to c squared as the foundational principle that we're talking about, if we see that a squared plus b squared is even less than what c squared would be, we know that c is bigger and it has a larger angle opposite it than a right angle, and it is an obtuse triangle. So since I don't have enough time, I'm going to have to give you a part 2, but it'll be short. We'll just talk about this last problem where we determine whether or not we can create a right angle triangle or a triangle at all, and whether it's acute, right, or obtuse. So stay with me. I'll be right back.